Welcome to the lecture on machine independent optimizations part 2. In the last lecture we covered global common sub expression elimination, copy propagation and loop invariant code motion. I also gave you an introduction to what induction variables are. We will continue that lecture today along with region based data flow analysis. So, an induction variable is actually related to a loop. Essentially the counter values in a loop are induction variables. The other variables which are dependent on the loop variables are also induction variables, provided they satisfy certain conditions. So, the basic requirement is the value only changes through an increment or decrement operation by a constant variable, a constant amount. So, there are basic induction variables which have the form I equal to I plus minus n, where n is a constant. Then there are derived induction variables such as j, which have the form c star I plus d, and they are defined only once within the loop. So, c and d are constants, essentially linear functions. So, if I goes as 1, 2, 3, 4, then j, let us say, is 5 star I, then it goes as 5, 10, 15, etcetera, etcetera. If it is 5 star I plus 3, then the first value will be 5 plus 3, 8, and then 8 plus 5, 13, and so on and so forth. For each induction variable we have a triple. For a basic induction variable, it is denoted as I comma 1 comma 0, and any other variable in the family of I is denoted as I comma c comma d. So, c and d are the constants. So, this means j equal to I star c plus d, that is how it would be read. So, here is the example from last lecture. So, I is an induction variable which is being incremented by 1 in the loop. T5 is a derived induction variable in the family of I, which is defined as 4 star I. Here is another example. So, I and j are both induction variables, both in the inner loop and this loop and the outer loop. Then T2 and T2 is an induction variable derived from I, is in the family of I, again both in this loop and the outer loop. Similarly, j is induction variable in the family of rather for T4 is an induction variable in the family of j, both in this loop and the outer loop. How do you detect induction variables? Basic induction variables are easy to find. You just scan the statements of the loop L. Whenever you have I equal to I plus minus n, they are basic induction variables. It is not necessary that basic induction variables are defined exactly once, they may be defined many times, but for derived induction variables in the family of a basic induction variable, the definition should be exactly once in the loop. Now, so search for variables such as k with a single assignment to k within the loop L, having one of the following forms. So, there are many forms j star b, b star j, etcetera, etcetera. So, what is not permitted is b slash j, because it becomes nonlinear. So, once we find something of this kind, we check for other conditions which need to be satisfied. So, just because k equal to b star j, it does not mean k is an induction variable. So, first we check if j is basic. So, let us assume we are looking at k equal to j star b. If j is basic, then k equal to j star b, and the triple for k is very simple, j, b and 0. So, similarly for other forms as well, if it is j plus b, then we have j 1 and b here. Okay. So, similarly for others, keep in mind that when you have I star I comma c comma d, it is I star c plus d, and we just put those constants here. The conditions are necessary to be checked when j is not basic. In other words, there is a basic induction variable I, and then j is in the family of I. So, its triple is ICD, and now we need to determine whether k, which is based on j, can also be said to be in the family of I. So, what are the necessary conditions to be checked here? Two conditions. First one is there is no assignment to I between the lone point of assignment to j in L and the assignment to k. Second condition is no definition of j outside L reaches k. So, let us understand these conditions slightly better. So, here is a basic induction variable I. Here is the definition of j, and j is in the family of I. Here is the definition of k equal to j star b, and it is supposed to be in the family of j. So, now the conditions 2b1 and 2b2 are satisfied here. So, let us see what they are. There is no assignment. Condition 1 says no assignment to I between the lone point of assignment to j in L and the assignment to k. Lone point of assignment to j and the assignment to k, between these two there is no assignment to I again. So, condition 1 is satisfied, and no definition of j outside L reaches k. So, there is no definition of j outside L which is reaching k, it is only this definition of j which is reaching this k. So, both the conditions are satisfied. So, in this example condition 2b1 is not satisfied. Let us see why. So, I is the basic induction variable as before, j is the derived induction variable in the family of I. Then here is the assignment to k, but there is an assignment to I as well. So, between the assignment to j and the assignment to k, there is an assignment to I. Now, the condition 1 is obviously violated. What is the problem? The problem is j is updated here, and now assignment to I is okay. We now have j star b. So, the old value of j is used here. So, there is no harm done. Whenever j is updated, the value of k is based on j and everything is okay. It is not dependent on I at all. But once we replace this assignment to k, which actually is a function of j, by a function of I, then whenever I changes here, this k value will also change. This is the difficulty. Here the old value of j is still available to me, even though the value of I has changed, but once I replace this j by j star b by a suitable function of I, because it is supposed to be in the family of I, then whenever I changes, k will also change. So, this will lead to a different program, and it may be an erroneous condition. So, semantic violation has occurred here, and therefore, this is not a valid transformation. We cannot say that we cannot actually base any transformation on this in particular information. So, we cannot say that k is in the family of I. In the last illustration here, condition 2b1 is satisfied. So, there is this assignment to k and this assignment to j, and there is no assignment to I in between. But condition 2b2 is violated. The reason is for this particular k equal to j star b, there is a definition of j which is reaching it from the outside, that is from b1, and there is another definition of j which is reaching it from within the loop. So, there are two definitions of j. So, both d1 and d2 reach this particular use of j. So, if j if this k which is dependent on j is actually replaced by a function of I, this dependence goes away and it could be a mistake. So, there is a semantic violation if we replace this by a function of I, and therefore, this transformation is also not permitted. So, this is the reason why these conditions have to be checked. How do we check these conditions? Fairly straightforward. If both j and k are temporaries in the same basic block, then checking conditions 1 and 2 above is very easy. So, we do not have to go beyond basic blocks. So, we just check the space between the two definitions of j and k, see if there is a definition of I, and then there is nothing else that is really going to cause problems. So, we are sure that j and k do not live beyond the basic blocks, that is the assumption here, j and k temporaries in the same block. So, there can be no definition of j which arrives from outside the block, they live only within the block, they are defined and they actually are not useful after the basic block. So, checking condition 1 is redundant, rather condition 2 is redundant. Otherwise, if they are not temporaries in the same basic block, then we need to find all the basic blocks on the paths from the point of assignment to j to the point of assignment to k, and then check condition 1. So, you have to find, look at all the paths, find all the basic blocks on the paths. So, every one of the paths must be taken, only thing is you do not have to go around the loops any number of times. So, you just have to go through the loop once and find all the basic blocks. So, and then that is it, then you can check condition 1 quite easily. Condition 2 can be very trivially checked using the UD chain of j in the assignment to k. So, this use definition chain will tell us how many definitions of j are coming to that particular, reaching that particular point. So, if there is more than one, then we have a problem and immediately condition 2 is violated. So, assuming that the conditions are satisfied, how do you compute the triple for k? The triple for j is assumed to be ICT, and let us say the form of assignment to k is k equal to j star b, and j is I star c plus d. So, make a simple substitution and find the constants. K becomes I star c plus d into b, that becomes I star b star c plus d star b. So, this is our c prime and this is our b prime. So, I comma b star c and comma d star b are going to be our is going to be our new triple. So, the b star c and d star b are constants and therefore, can be evaluated by the compiler. So, that is how we get the new triple for k. So, if there is the next induction variable dependent on k, we know how to convert it and make it dependent only on I. So, now the next transformation that we need to understand is strength reduction, and after this we will look at induction variable elimination. So, consider each basic induction variable I, and for each induction variable j in the family of I, let us say its triple is ICD, we want to actually reduce the strength of j. If it is 4 star j, we want to actually replace it with by some addition operation. So, to do that we create a new variable s. So, let me give you an example of that and then go back to the algorithm itself. So, here we have the basic induction variable I, which is incremented I equal to I plus 1 etcetera. T5 is the induction variable in the family of I, it has 4 star I. So, assuming that star is a costly operation and it needs to be replaced by a simpler plus operation. After transformation, it becomes T5 equal to T7 and T7 equal to T7 plus 4 with an initialization of T7 equal to 4. So, there is no 4 star I anymore. So, there it has been replaced by an addition. So, that is why in the example we had T7. So, similarly, we have a new variable called S. This is for each of the derived variables j, okay, which whose strength reduction has to be carried out. replace the assignment to j by j equal to s. So, we did that here. So, we replace T 5 equal to 4 star I by T 5 equal to T 7. And if there are two induction variables j 1 and j 2 with the same triples, that means both of them advance with the same constant value, then we can use a single variable for these two triples together. Now, immediately after each assignment to I, that is I equal to I plus n in L, where n is a constant, place the assignment s equal to s plus c star n. C star n is a constant, obviously, this is the n we are talking about. So, whenever I is incremented, we are also incrementing s by the appropriate amount c star n, because whenever I increments, j will also increment by the appropriate quantity. So, that is what we want to do here, s equal to s plus c star n. So, for example, it was 4 star j, j equal to 4 star I, as I goes 1, 2, 3, j goes 4, 8, 12 and so on. So, now that means addition of 4, that is what we are doing here, add c star n. So, here we have placed T 7 equal to T 7 plus 4 immediately after this statement I equal to I plus 1. So, because this constant is 4 and so this is 4 I comma 4 comma 0. So, we have and this is I equal to I plus 1. So, 4 star 1 is 4. So, T 7 plus 4. Place S in the family of I with the triple ICD. So, we have actually S is nothing but j, okay. So, it is just a replacement for j. So, its triple is identical. We have replaced a costly star operation by a cheaper plus operation and place the code to initialize S to C star I plus D at the end of the pre header. So, we did that here, T 7 equal to 4. So, C star I plus D is 4 star I plus 0, that is 4. Okay. So, this is how the induction, the strength reduction has happened. So, let us take another simple example. So, this is example 2. We had for example, let us look at this. Yeah. So, we had T 2 and T 4 which are dependent on I and j respectively. So, those have been replaced. Okay. So, now we have S 2 equal to S 2 plus 4 instead of 4 star I and S 4 equal to S 4 minus 4 instead of 4 star j. The reason this has become minus and this is still plus is this is I equal to I plus 1, whereas this is j equal to j minus 1. Okay. So, the n is minus 1 here, that is why this has become minus 4. So, and then there is initialization S 2 equal to 4 star I and S 4 equal to 4 star j. So, and these two statements S 2 equal to and S 4 equal to have been placed immediately after I equal to and j equal to. So, this is a very simple strength reduction operation, star has been replaced by plus. So, this strength reduction happened within this loop and within this loop respectively. Now, we did all this with a view to see if we can finally eliminate the induction variable. The idea is, in this case, okay, here T 5 increments by 4 in a very loop, whereas I increments by 1. So, wherever we have the test for I, if we are able to replace it by the test for T 5, then it is done. So, the first step in that process is to do strength reduction and then do induction variable elimination. So, let me give you the same example here. So, this is the old example and we replaced this this T 7 equal to T 7 plus 4 has replaced that T 5 equal to 4 star I. So, we do not have that anymore and now I is ready to be replaced by T 7 itself. So, instead of I greater than 100, can we put T 7 greater than something? Yes, but T 7 increments by 4 at a time. So, if I is compared with 100, T 7 must be compared with a quantity which is 4 times that. So, that is what we do here, T7 greater than 400 instead of I greater than 100. The rest of the loop remains the same, and that is when we have got rid of this statement I equal to I plus 1 can be deleted. How to do this systematically? So, consider each basic induction variable I, whose only uses are to compute other induction variables in its family and in conditional branches. If this is so, we can eliminate this induction variable. Now, consider j in I's family with the triple ICD. So, we want to remove I and replace it with j. If there is a relational operation I, if I rather conditional statement, if I rel of x go to b, we want to replace this I by j, which is in the family of I, then what is the replacement for x? So, if I is j is this I is becomes I star c, x should become x star c. If this becomes I star c plus d, this should become x star c plus d. So, I star c plus d is j and x star c plus d will be computed and that will be put into the variable r. So, that is why if I rel of x go to b is the conditional statement, we replace it by r equal to c star x, r equal to r plus d. So, that updates x appropriately and makes it dependent, makes it get a value comparable to j, and then we write if j rel of r go to b. So, this is the transformation, and there is a small hitch here. What if c is negative? In other words, what if we have I equal to j equal to minus 4 star I. Okay. So, I increases 1 2 3, but j will decrease in the negative direction minus 4, minus 8, minus 12, etc., etc. In such a case, replacing this j I rel of x by j rel of r by this transformation would become incorrect. Let us take a simple example. So, if you had minus 5 less than minus 2, it is a correct statement, right. Now, change it to plus 5, 5 less than 2 is obviously wrong. Similarly, if you had 5 greater than 2 and now you change it to minus 5 greater than minus 2, that would be incorrect. What we need to do whenever we change the sign is to complement the relational operator as well. So, if you have less than, you must replace it by greater than. If you had less than or equal to, then you must replace it by greater than or equal to, and so on and so forth. So, if c is negative, then we use rel of bar, that is the complement of that relational operator, in place of rel of in the above code sequence. So, for example, if c is minus 4, then if I greater than or equal to x go to b is replaced by the code sequence r equal to minus 4 star x, r equal to r plus d, and then if j less than or equal to r go to b. So, this would be a correct replacement for if I greater than or equal to x. So, this is based on the assumption that we know the direction in which the decrement or increment is happening. So, the sign of c. That is why we always insist that c and d are constants. In theory, they could be loop invariant condition, values. The values come from outside, but if we do not know the sign of that particular value, then this elimination of induction variables is not a possibility. We must know the direction in which the values increase or decrease, that is the sign of this constant c, otherwise we cannot do anything about induction variable elimination. Then we delete all the assignments to the eliminated induction variable in the loop, in this case I, and apply copy propagation to eliminate statements of the form j equal to s if necessary. So, here we did this replacement, instead of I greater than 100 it became T7 greater than 400, and that is about it. Then the second example, instead of I equal to I plus 1 T2 equal to 4 star I, we did strength reduction, it became S2 equal to S2 plus 4, but why do we have to keep I greater than or equal to j here? So, j has been replaced by j equal to j minus 1 and T 4 equal to 4 star j are the other two statements. So, T 4 equal to 4 star j has been replaced by S 4 equal to S 4 minus 4. So, can we replace I greater than or equal to j by S 2 and S 4 respectively? It so happens that we can. It is just that it should be the inverse of the condition. So, S 2 not of S 2 greater than or equal to S 4. So, if we have that, then go to B 6 works perfectly okay here. So, this is the way we actually do induction variable elimination. Then let us take a running example starting from looking at the old program that we had. So, we really have several induction variables here, they are all listed here. I is also one of them, but let us ignore I. Let us look at j only and its derivatives. J is a basic induction variable. So, j 10 is its triple. Then we have T 4 equal to 4 star j here. So, that is a derived induction variable in the family of j with j 4 0. Then T 6 is j plus 1. So, that is another derived induction variable with the triple j 1 1. Then T 7 is one more, it says 4 star T 6. So, it is in the family of T 6. So, T 6 4 0, but T 6 itself happens to be in the family of j. So, T 7 is also in the family of j with the triple j 4 4. Okay. So, now these are the induction variables that we have detected in this loop. Now, let us do strength reduction. So, in the here T 4 equal to 4 star j was replaced by T 4 equal to S 4 and S 4 equal to S 4 plus 4, and then T 6 equal to j plus 1 was replaced by T 6 equal to x 6 and S 6 equal to S 6 plus 1. T 7 equal to 4 star T 6 was replaced by T 7 equal to S 7 and S 7 equal to S 7 plus 4, and then appropriate initializations were all carried out in this particular pre-header. So, this is a strength reduction. Now, after common subexpression elimination and copy propagation, so for example, all this T 4 etcetera becomes S 4. Okay. So, these are the copy propagations that have taken place. So, A of S 4, A plus S 4, A of S 7, A plus S 7 etcetera etcetera. So, then after we did this, so where was so here we had 4 star j 4 star j. So, these are two common subexpressions. So, those were also removed, and that is why CSC is mentioned here. Okay. So, a little more efficient code. Finally, removed the useless code that is corresponding to the I and did induction variable j elimination. So, we had in this for example, we had if T 3 equal to j less than T 2 and if not T 3 go to B 3 or B 8. So, that was replaced by T 2. So, S 2 became 4 star T 2 and T 3 equal to S 4 less than S 2. So, we replaced for example, j by S 4 and T 2 was replaced by its appropriate multiplicand, that is S 2 4 star T 2. Okay. So, that is how the induction variable elimination took place. So, now this becomes not of T 3, it is not dependent on j anymore. Okay. So, the quadruples for j were all removed and only those which are required S 4, S 7 etcetera were retained. So, this is a detailed example of how induction variable detection, then strength reduction and induction variable elimination happens for a non-trivial program. So, that is as far as some of the basic optimizations are concerned. So, let us look at a very interesting version of data flow analysis called region based data flow analysis. So, in the so one of the previous lectures we talked about iterative data flow analysis. So, in which the basic blocks were all traversed in particular order to find a solution for the data flow analysis problem. Whereas, here we divide the control flow graph into regions. So, we looked at regions very briefly. So, let us recapitulate what exactly regions are. So, a region is a set of nodes n that includes a header which dominates all other nodes in the region. All edges between nodes in n are in the region except for possibly some nodes, some of those which that enter the header. So, it is very easy to give you some examples of this. So, let me go a little further. So, here for example, if this is the big region and when we are constructing the yellow region outside this. Okay. So, the arcs AC and AD are not in the region U, they are in the region V. Okay. So, when we consider region U, we do not consider these two arcs, we will consider it only when we go to region V. So, all intervals are regions, but there are regions that are not intervals. So, a region may omit some nodes that an interval would actually include, or they may omit some edges also back to the header. So, for example, the interval for 7 was 7, 8, 9, 10, 11, but 8, 9, 10 could be a region. So, let me show you that example. So, I 7 is 7, 8, 9, 10, 11. So, this entire thing, right, but just this 8, 9, 10 could be 8, 9, 10 is just this region. Okay. This could be a region on its own. So, 8 dominates 9 and 10. So, that is how this becomes a small region on its own. So, a region may have multiple exits. So, this region 8, 9, 10 has 2 exits. So, no problem. Now, what we are going to do is we will compute gen of r comma b and kill of r comma b of definitions generated and killed along the paths within the region R from the header to the end of the block B. So, this will become clear as we go along. So, this is the interval graph that we had already looked at, right. So, this is interval 1, 2, 3, then this reduces further and so on and so forth. And this was the other interval graph. So, interestingly, if you look at 3 as the header, then this 3, 4, 5, there is a minor change here in the graph from instead of this we made it that, right. So, this changes the interval structure. So, 3, 4, 5, 6 become an interval and rest of it 7, 8, 9, 10, 11 become another interval and finally reduction takes place. So, each of these could be a region actually. Okay. So, no problem, an interval could be a region. So, this is an example of how regions are, or each of these could be a region. Okay. So, there are 4 regions in this example and 3 regions in this example. So, what exactly is region based data flow analysis? The basic idea is to define a transfer function called trans of r comma b with a parameter s. So, this will tell us that for the input s, okay, which is a set of definitions, we are looking at reaching definitions problem, let us say. So, for any set s which is sent as a parameter, that is a set of definitions for in this example, what subset of definitions reach the end of the basic block B by travelling along paths wholly within R. So, this is important, we are not looking at edges which are not in the region, assuming that all and only definitions in S reach the header of R. So, there is no other way of reaching the header of R. So, only the definitions in S will reach the header of R, and then how do they travel inside the region R is what is captured by this trans function. So, trans of r comma b with the parameter s would be whatever is generated within the region R, okay, that is gen of R comma B for that basic block B and reach the end of the basic block B, union S minus whatever is killed by the basic block B with respect to the region R. Okay. So, if you look at the entire region and let us say trans of u comma b, and then let us say the incoming set of definitions is phi, that was the initialization we always had, that becomes our out b. Okay. So, this is the out function we defined in iterative data flow analysis. So, here is the connection between the region based data flow analysis in which we want to find trans functions and the out functions that we have in iterative data flow analysis. So, this out b is nothing but gen of u comma b, because S is phi here. Okay. So, phi minus something is phi. So, gen of r comma b becomes gen of u comma b with r equal to u, where u is the region consisting of the entire flow graph. So, basically we need to provide a method to compute the transfer function trans of r comma b for progressively larger regions defined by some T1 T2 transformation of a control flow graph. So, you could use interval methods and define regions. In our example, we are using T1 T2 transformations to define regions. And since out b is gen of u comma b, we need to compute only gen of r comma b and kill of r comma b for the basic blocks. These are needed for computing gen for progressively larger regions. We do not have to compute in b function at all, it is not necessary in this approach. So, there are a couple of observations here before we take up an example, but let me show you this structure. So, here is our control flow graph for which we are going to do region based data flow analysis. At the innermost level are the regions A, B, C, D. When we combine them using T2 transformation, so we get regions T and R. When so this edge D to C is outside the region R, and when we apply the T1 transformation, we get on this region R, we get region S. Finally, when we apply T2 transformation between T and S, we get the region U, and the edges from D to A and C to A are not part of U, but they are part of V. So, we need to apply T1 transformation on U in order to get V, and V is the final. So, we are going to start our region based data flow analysis from the basic blocks, grow the regions. This hierarchy of regions is provided by the T1 T2 analysis. So, as we perform the transformations of T1 and T2, we keep track of the regions as well. So, we compute the gen information for the basic blocks and then provide a method to compute the gen information for the T, R, S, U, V, etc., when we perform either the T1 or T2 transformations. So, as we reduce the flow graph G by T1 and T2 transformations, the following conditions are true at all times. A node represents a region of G, an edge from A to B in a reduced graph represents a set of edges. So, this is clear. So, for example, this edge, okay, S to T. So, we have S here and this is T. So, this is already something I told you. So, these are the two edges corresponding to one edge in the bigger reduced graph. Each node and edge of G is represented by exactly one node or edge of the current graph. So, in the reduced graph, okay, so there is representation, each node and edge of G will be represented by exactly one node or region. So, you can't have a node of this graph G in say A, it cannot be present in more than one region of at any point in time. Okay, it can be a part of exactly one region. So, the same is true for an edge as well. An edge cannot belong to two regions at any point in time. Okay. So, region based DFA can be compared to syntax directed translation, with the structure being provided by the hierarchy of regions. So, in other words, let us say we are trying to generate machine independent code quadruples for expressions. So, we start from the lowest level, look at the expressions, and then if it is A star B plus C, we generate code for A star B, put it into a temporary, then use that T plus B, generate code for T plus B, and so on and so forth. So, this is the syntax directed translation. So, the similar thing is done in the case of region based analysis also. So, the regions grow bigger and bigger. So, just like the tree becomes, syntax tree becomes bigger and bigger, and from inside that is corresponding to the leaves, that is the basic regions here, we go to the outermost region, that is the root of the syntax tree, we actually compute the data flow information. So, we consider the data flow analysis for reaching definition in this particular case, and immediately afterwards we will see how to do available expression analysis as well. It should be emphasized that all data flow values which reach the header of a region will surely flow to all the constituent regions and basic blocks, since all basic blocks are reachable from the header of the enclosing region. So, what we are trying to say here is, in each region there is full connectivity. So, the header of any region can reach any node in that particular region, there is connectivity. So, if some information reaches the header of a particular node or region, then it will definitely flow to every node in that particular region, the smallest node as well. Okay. So, that is what we say here. This is very important, this connectivity information, because the only way we can enter a region is through the header, and if the header is not connected to some node, then information cannot flow. So, our basic assumption is that so you can reach every node in that particular region. So, but region formation itself ensures this. So, there is nothing to worry. There are two transformations T 1 and T 2. So, for each of these transformations, so now we provide a method of computing the transfer functions. So, as I told you, we need to compute only the gen and kill information for each basic block corresponding to each region. So, from the lowest level to the highest level. For the basic regions, that is the basic blocks, so gen B is what we know how to compute, kill B is another quantity which we know already how to compute from iterative data flow analysis. So, gen B of B comma B, the instead of gen R comma B, that is the lowest level, gen of B comma B is nothing but gen B, and kill of B comma B is nothing but kill B. With this information, let us take a region such as R, which is built by a T 2 transformation from the regions R 1 and R 2. So, R 1 has been built before, R 2 was also built before, now there is an edge between R 1 and R 2. So, we can collapse R 1 and R 2 and make it a single region R. So, this was the transformation which was applied. Now, the structure is available to us, how exactly the transformation happened. So, given the transfer functions gen and kill for R 1 and R 2, how do we compute the transfer functions gen and kill for the region R for the same basic blocks B in these two? Okay. So, region building by T 2. Suppose you consider the basic blocks within the region R 1 such as B. Okay. There are many basic blocks, we have shown only one. R 2 does not affect R 1 because there is no path to go back to R 1 within this region R. Okay. You cannot go from R 2 to R 1 within this region R. The only connection between region R 1 and R 2 is this particular edge, which may correspond to more than one edge, okay, in the actual control flow graph, but there is no back edge, nothing, you can't go back. That is the way it has been constructed, the regions have been constructed. Therefore, since R2 does not affect R1 at all, the gen of R comma B, that is the gen of with respect to region R for the basic block B, is same as gen of this particular B with respect to R1. So, that is R1 comma B. Similarly, kill information is also the same, kill of R comma B is same as kill of R1 comma B. Now, this is what I was saying, edges from R2 to R1 are not part of region R. So, we do not have to worry about going from here to here. If you look at basic blocks within the region R, they are definitely affected by region R2, sorry, within the region R2, they are affected by the region R1. But which blocks in R1 affect R2? Since the connection is only just this, right, the only blocks which can affect R2 are if this edge corresponds to, let us say, 3 edges, there will be 3 blocks connected to those 3 edges here. So, those are the only 3 edges which will hurt R2. So, let us take this same example. So, here T and S, there is a connection, this C is the header of the region S. So, there is an edge from T to S, C and A to C. So, this is the region, the T corresponds to R1 and S corresponds to R2. So, these are the only two basic blocks, rather regions from which we can enter C, right. So, therefore, we need to consider blocks corresponding to the predecessor of the header of R2. So, here for example, this is the header of R2. So, we want to look at the predecessors of the header of R2. So, those are the two blocks A and B. So, gen of R comma B now will be gen of R2 comma B, whatever is generated by B with respect to the region R2, union G minus kill of R2 comma B. What is G? G is union of gen of R1 comma P for all predecessors P of the header of R2 in R1. So, those are the blocks I was talking about. Header of R2 is here. So, there are many predecessors. So, take all those predecessors, they are the only ones which can hurt R2. So, take the union of the gen of all those predecessors, they will all be able to reach the header of R2. So, that is the set G. So, from that set G, remove whatever is killed by this R2. So, kill of R2 comma B, killed by B with respect to R2. So, and add gen of R2 comma B generated by B with respect to R2, then you get the whatever is generated by B with respect to the region R. So, this should be clear. So, kill is very similar, kill of R2 comma B union K minus gen of R2 comma B. So, where K is intersection of kill of R1 comma B P. Why? If there are many predecessors like this, okay, unless the definition is killed along both these paths, we do not take it as killed. That is the reason why we take the intersection. For generation, it can reach along any one of the paths, but for killing it should be killed along all paths. So, that is why this is an intersection and this is a union. What about the transformation T1? T1 is like this, there is a region R1, there is a self loop, so and we want to get rid of it. So, that is the transformation T1. So, if you look at the kill set for the region R, it is same as the kill set of the basic block B with respect to R1. Why? A definition gets killed going from the header to B if and only if it is killed along all acyclic paths, and hence back edges such as this incorporated into R will not cause more definitions to be killed. So, from the header here along every path to B, the definitions are killed. So, those are the kill definitions that we already know of. So, this back edge will not create further problems, and therefore, kill of r comma b is nothing but kill of r1 comma b. So, whatever gets killed from the header to b is kill of r1 comma b, and that is precisely kill of r comma b as well. Nothing more can be added by this. Whatever is killed along all paths is already taken. So, bracket will not add extra information. The same is not true for the gen set. So, there may be gen of r1 comma b union g minus kill of r1 comma b is gen of r comma b. Why? G is union of gen of r1 comma p for all the predecessors. So, it is possible that some definitions here come we are looking at all possible paths, and any one of these paths can generate a definition. It is unlike kill. So, maybe from here I go back and then take some paths which comes here, that could be generating a definition for us. Okay. Whereas, in the case of kill, every path was covered. Here not all paths are covered, any one of the paths is good enough for our generation. Therefore, we need to look at all the predecessors of this particular edge. This is a compound edge. So, there may be many predecessors corresponding to this compound edge. Look at all of them and then take so to give you an example here, in this region V we had a self loop. So, these two edges corresponded to a single compound edge. So, we had for this header we had two predecessors C and D, okay. One was this and one was that, and both these together corresponded to a compound edge. So, this compound edge. So, we take the predecessors of this compound edge, and when we actually travel along this edge, they may actually reach the header of R1 and then further reach B. That is the reason why we take the union of all these predecessors, gen sets of the predecessors, and then remove the whatever is killed by this basic block, add the whatever is generated by this basic block, and that gives us gen r comma b. So, this is very similar to what we did in the T2 transformation, but this is different because of this particular reason. So, this is very similar. So, we take the predecessors and then they can all come here possibly along any one of the paths. So, here is an example. So, region based analysis. So, we have all the regions here that I showed you. Let us say there are 4 blocks and here are the gen and kill sets, okay, and here is our control flow graph. So, for example, if you are building region R, okay, from C and D by T2 transformation, gen of R comma C is gen of C comma C. This is at the lowest level. So, it is same as the gen and kill sets, kill is similar. The header of D is just D, okay, and header predecessor of D in C is just the node C. So, this is a T2 transformation, we are computing G and K. We are looking at the predecessors, that is there was only one which is C. So, we get gen C comma C. This also becomes only C, kill of C comma C. Now, for the bigger region R, gen of R comma D, from the equation is gen of D comma D union gen of G minus kill of D comma D, that gives us 0 0 1. Similarly, kill of R comma D is kill of D comma D union K minus gen of D comma D, that gives us 0 1 0. Now, we apply the T1 transformation to get region S from R. So, there is only one predecessor for this header node C, which is D, okay, within S. So, this is the edge we are looking at, this is D. So, G is gen of R comma D, R is this region. So, 0 0 1 as we computed before. So, gen of R comma D is 0 0 1, okay. So, the kill set is not modified, it is same as that of R comma C. So, that is written here, and the gen set is computed using that formula gen union G minus kill. So, we get the appropriate 0 0 1 and 0 0 1 for the C and D nodes with respect to the region S. Then we have building region T, that is this, which is very similar to building region R. So, let us not spend too much time on it. We get similarly gen of t comma a, kill of t comma a, g, k, gen of t comma b and t comma b. This is very similar to what we did for C and D to build region R. Then we want to build the region U from T and S, this is by T2 transformation. So, these two A and B will not be modified too much, because this corresponds to region R1. So, they are as it is, they are as they are. Whereas, for this region yes, okay, it is different. Okay. So, the header of S is C and predecessors of C are B and A. Okay. So, there are two nodes here. So, because of that we have to compute G and K with these two predecessors, gen union gen, okay, A and B, kill is intersection A and B. So, we get this, then apply the gen equal to gen union G minus kill formula and obtain these 4 quantities. So, then we build the region V from this from U, rather this is a small mistake, from region U by T1 transformation. The header of U is A, okay. So, this entire this and predecessors of U in U are C and D. So, these are the 2, okay. So, now we need to compute the G function using rather G set using the 2 gens, and finally compute gen of V comma A, V comma B and so on and so forth. Finally, to compare the iterative approach and this region based approach, I have listed here the out and in sets for the iterative data flow analysis, and in the 4th iteration there is convergence, and we produce exactly the same information as in the iterative data flow analysis. So, these two actually are identical, it is just that there are 2 different approaches for the same problem. So, the available expression elimination rather available expression analysis problem is very similar. It is just that in this particular case the gen and kill definitions become G equal to intersection and K equal to union, because available expression information has this. So, we will stop at this point and continue this example in the next lecture. Thank you.